cloud for now.
All right.
So
welcome, Dimitrios. I think that Dimitrios needs very little introduction, but Dimitrios is professor of computer networks and director of the Network Systems and Cyber Defense Laboratory in Glasgow University. And he's going to be talking today about digital resilience and the critical national infrastructure. So, Dimitrios, the room is yours.
So, thank you very much. Thanks, Ignacio. Just confirmation that you guys can all see my full screen.
Yes.
Excellent.
Yep.
Right. Any hiccups in the slideshow? Just shout, because now I've lost the picture of everybody. So I'm just looking at my slides. So thanks very much, Ignacio and Shant, for the invitation, and good to see you, colleagues. Thanks for coming. So yes. So hopefully many people will know who I am. And the reason I'm here today is that earlier this year was very privileged to have been awarded a Royal Academy of Engineering Research Chair to address the topic of digital resilience for critical national infrastructure. And this is great. Delighted, not least because it's one of these topics that, you know, are less, you know, traditional engineering, the way, for example, the national academies see it. You know, if you see other awardees, the subjects are more around, you know, materials, chemicals, and so forth. So being, you know, digital resilience being acknowledged as a topic that deserves the attention of the National Academy was great. So we had a strong consortium which comprised our partners from DSTL, Defense Science and Technology Laboratory, but also CNIF. CNIF is the CNI forum that comprises all the civil nuclear UK licensees. So two critical national infrastructure operators came together with us to put a very good, a very strong bid in, and we were delighted to have been awarded the chair. So, you know, news got out, and then I came to Cozeners and met Nishant and other guys, and said, why don't you tell us all about it? So here I am to tell you all about it, or as much as I have about it. I appreciate this is a new program, so what I thought I would do is to tell you a little bit about what we propose to do and what we want to do and why, and then touch on a couple of projects that we've done, mainly over the past year or so, to give you an idea of the kinds of things we have been doing and building on, and we will be doing for this program. So. So let's give a little bit the sort of research context. So digital resilience for critical national infrastructure. So what is resilience? There's many definitions, but among those definitions, one also supported by NCSC is the ability of a system or a device or an organization to recover and adapt following attacks, and contrast to the sort of more traditional definitions of cybersecurity, for example, that tries to prevent attacks. In resilience, we assume that, you know, bad things and attacks will happen, and therefore how we get out of these and remediate their effects. Now, CNI in particular is harder to do this for a number of reasons. First of all, it's becoming increasingly digitally enhanced and interconnected, and this comes as a sort of sudden connectivity for CNI, because CNI comprises the sort of industrial control systems and what we call IT/OT technology, or IT, obviously we know it is operational technology, environments that were not designed to be connected to anything very smart. Now, you know, increasing interface between generic ICT capability that becomes more smart and OT environments opens up all sorts of opportunities to modernize CNI. and benefit economy and automation and all that. But at the same time, this means that it gets also increasingly exposed to cyber attacks and adversarial events. And in this short clip here, you see such an attack that happened last year, June 2022, in a steel manufacturing plant in Iran, where adversaries interrupted the steel molding process with these effects that you see. And not only that, they also hijacked the IP camera that was looking at the plant to make sure it was captured. But on a more serious note, so now you realize that in CNI systems and these kinds of industrial control systems, when these things happen, we're not just talking about losing our data, but we're talking about potentially losing lives and interrupting serious industrial processes. Now, protecting the dynamic operation of these environments is problematic, however, and there is many reasons why it's problematic. One of them is safety. And safety, we understand, is completely different from security, and the safety function of a maritime platform or a nuclear power plant is of primary importance. And anything that changes the safety case of a running process is a no-go. So patching is complicated. The vendor dependence of these environments, as well as the prolonged lifespan of systems that operate in the OT space, can be 20, 30 years of age, and also the resource constraints they operate in make it very hard to patch it the way we patch our laptops and so forth. There's other things on data sensitivity and performance, obviously, of industrial control processes that play. The other thing is that the standards and regulations that govern these environments, and there are many, as we'll see later on, they mostly focus on design time component properties that can be, are well understood and can be described and quantified, if you like, more than the sort of more dynamic properties of such systems that are a little bit less known and less predictable, and therefore less easy to describe. So this is what makes the job of making CNI more resilient complicated. So what we suggested and to how we go about it is what follows. So we suggested a holistic program of work to ensure that the systems and organizations that underpin CNI are resilient against a dynamically evolving set of threats that manifest through the digital, both at their onset, when they happen, but also over the longer term. And also to be able to retrofit digital resilience to systems that were not built with resilience in mind, but they're not getting replaced or going anywhere anytime soon. So, and we propose that this approach we structured around three main angles. One is the measurement and control instrumentation of digital systems and enhancing this. The other one was to use data that we get from those systems and use tuned processes to enable the timely diagnosis of adversarial events. And timely might not be at the microsecond level, but still it's at short time scales. And then also see how any mechanisms we devise become part of the organizations that run these systems. So those of you who are familiar with work that was mainly led by colleagues from Lancaster University, and I also had some involvement in the past, you will know this D square R square plus DR framework that tries to put the resilience properties and phases, if you like, in a sort of more systematic way. You see obvious analogies with the different phases of the NIST framework, for example, but also a sense of things happening at the onset of adversarial events to defend and detect them, but also the sort of offline, always on processes to diagnose and refine the operations of those systems. So let's look a little bit in each of these themes and what we want to do. So in terms of measurement and control instrumentation and enabling the network systems of these environments to do this and be able to then detect and remediate attacks. So we want to make resilience more built-in rather than bolt-on, which currently is, and the same for cybersecurity. And these environments, as I said, as we're moving to more zero trust, more environments with less of a hardened perimeter in the sort of traditional protection of these systems. These are environments with very low network visibility, so installing monitoring capability in these environments is not trivial. So we want to enable resilience capability for every element, but at the same time without having to instrument every single element. You appreciate why. So we want to use the network as a sort of natural aggregator that it is, because it sees the traffic coming to and from these environments from the digital. And at the same time, even though I'm sure you appreciate this diagram and you know what it means, so we know of advances in networking over the past 10 or 15 years that allow us to enhance this sort of switching functionality of these systems and add more capability and programmatically as well. And I'll say a little bit about this later on. But these environments, these systems, we're not talking about your Tofino switches. We're talking about industrial Ethernet switches and single board computers and mini PCs or these types of capabilities. So in these environments and in these architectures, enabling high-speed network monitoring and instrumentation capability becomes challenging, even though, as I said before, high speed in these environments doesn't mean hundreds of gigabits that we see in backbone networks. And also makes it challenging how to do sort of dynamically extensible, how to enable dynamically extensible resilience functionality. So how can we protect not just from a fixed set of things and attacks, but also extend to things we don't know into the future. And why we want to do this as part of the network is because we probably cannot afford not to. If you look at this, any sort of functionality that you want to do on a per packet basis, essentially, if you're looking at the network, you see that. So this graph shows here bar plots of a very simple wire function. Implementing it using the DBDK bypass, a bunch of different XDP hooks, and also userland, and you see that there is an order of magnitude difference here in the latency of the RTT. So, and then as I said, yes, all this we want to do in a sort of resource-constrained environments and devices. Now, the second theme is looking at data-driven resilience algorithms. So, if we enable this instrumentation that will allow us to monitor all those things, and I'm talking about the network, but I'm not talking exclusively about network data. I'll give examples later on. How can we then take advantage of these and use all these advanced machine learning algorithms we all get familiar with these days to do timely detection of adversarial events? And are we going to be able to use this for formulation, for attribution? It's a very, very manual process these days. And can we do normal behavior profiling and fingerprinting in these environments? And what we see here is a few graphs from prior and the existing current work that is looking into this. And I've just picked some graphs that show how monitoring different things and analyzing the data of different things can give you different ideas of things going wrong. So a simple EWMA monitoring that you can do at line rate if you're do it as part of your network stack can tell you fairly quickly when you have a fault, like an interface goes down. But then here we did some work to show again how devising sort of lightweight anomaly detection algorithms, in this case Shannon entropy and DWMA combined can give you similar accuracy of detection of a denial of service attack happening, but again, an order of magnitude almost faster than if you did more complex analysis that would have to go through the cloud. And here a more recent and more relevant, if you like, work more relevant to these environments we want to look at is a multi PLC system with a fan that gets started to cool down, a hypothetical plant, and of course it starts based on the readings of a couple of sensors, and you've got two fans to cool this down, to cool the motor down, and there you've got an adversary that connects to the switch of the OT environment and tries to attack this and basically not let the fans come up, and therefore the motor overheats and so forth. And we've demonstrated this in our sort of testbed in a box or testbed in a suitcase that you see here. And here we looked at, as I said, diverse data sources, so network data, memory artifacts of PLC, etc. And we just graph metrics like distances, etc., to see if we could make sense of normal behavior versus abnormal behavior, and you can see here the different shapes that the sort of normal behavior has, and the different clusters that are formed when these things are looked at in combination when an anomaly happens. So the challenges we want to address here more generally is the sort of the diverse data and how much we can make out of trying to harness diverse data feeds, like from network data, PLC data, CTI feeds, and so forth. and all this is great, so long as any technology we devise can be part of the organization that operates these systems. Okay, so any smart devices we might develop, any smart algorithms we might develop. How do we make organizations? How do we enable organizations to then start using them? And as you know, this is a complex process because organizations integrate technology, operators. In this case, for example, SOC operators and incident response teams, and they operate in a broader context of an organization. So, how much automation we can facilitate, or how much we can increase automation, for example, in incident response. You appreciate this is very hard, because there's reluctance in fully automating these systems. A network operator, will not just shut down part of the network because the systems tell them they want to have accountability, let alone a CNI operator. And when we increase complexity with whatever systems we put in, we also increase the risk. And especially nowadays, when our algorithms move from more deterministic to more statistical confidence, how you can assure an organization that when an algorithm says that you've got 90% confidence that this is an attack, actually they should do something about it. And beyond that, there is the organizational framework. Organizations have procedures and policies, and also, especially in this context of CNI, operate under a regulatory framework. And regulators want to make sure that organizations adhere and comply to various standards. So I'm sure you're familiar with the various cyber assessment frameworks, the UK from NCSC, and the security assessment principles, like the ones from the Office of Nuclear Regulator, and so forth. So how do we take these into account? And how do we make organizations more resilient by enabling the use of our technology? So if I take this a little bit further, sort of try to explain what I mean. So this is, you see here a table. This is not our work, by the way. This is work from again, colleagues from Lancaster, that you see the citation down here. It's a paper that looked at devising a cyber incident response and recovery framework. And in doing so, they analyzed a long list of standards from the UK, from Europe, internationally, and they did a very nice systematic breakdown of requirements and properties of what these standards cover in terms of this incident response and recovery framework. So I appreciate there's lots of acronyms here that are unexpanded, but here, for example, you've got technical and non-technical, or non-technical and technical, if you like, requirements and coverage in these standards. Then you've got planning, preparation, mid-incident, post-incident response phases, and you see how when we move, first of all, in general, the sparsity of these matrix increases as we move to the right, and as we move into the mid-incident phase of phase that during an incident, you see that properties like resource availability or other incident recovery and evidence collection and handling are much more sparsely populated. So how can we get technology to basically enhance this kind of coverage? So as I said a little bit earlier, the sort of guidance and standard focus on properties of systems and organizations that we can broadly or crudely, if you like, separate to static and dynamic. Static being ones that require compliance during the system design time and remain relatively unchanged unless the system changes. And there is relatively detailed coverage, even though not always, and a good understanding of what the expectations are to meet these standards. So if we look at some extracts, from example, this one is the IEC 62443 standard, and these are requirements for network segmentation. These are requirements for cabling extracted from a NIST SP800 standard. Requirements for device authentication extracted by the Health and Safety Executive Operational Guidance 86 standard. Coming into dynamic properties is more like things that change through the life cycle of a system and might have to do with malware protection and analysis extracted by the same IEC standard, or intrusion detection and prevention, or security monitoring, data capture and distribution. And what we see here is that some of them are very brief. Okay, essentially saying, ensure that no malware is going around your system, or ensure that your monitored data is stored and sent to a server for further analysis. And one could argue are relatively short. So it's a section you have on cabling that says quite specifically the different types of cabling that are better or worse for plant systems, fiber and RJ45 connectors and all that. This more or less the same amount of requirements tries to describe the need for IDS, again at a very high level. So on the static requirements, we need to better address how legacy systems need to be adapted to increase the resilience, whereas in the dynamic requirements, we need more detailed guidance with clear criteria and sort of thresholds of what is this exactly that we try to comply with, and what is going to be good enough, if you like. Okay, so let me now go a little bit get a little bit more technical and then say where we're coming from and how we will aim to address the sort of some of the technical aspects of the work to be able to then also meet and feed back to organizational requirements. And some work we did over the past few years. So you see this paper is already now just over 6 years, 6 years old, was on programmable data planes to increase or rather enhance the functionality of devices en masse. So devices that don't need or cannot afford, hardware acceleration and chips designed to execute a certain language very fast, but rather do sort of device and protocol and platform and language independent programmability. I don't want to say too much about this, but where I guess most of the community was looking at P4 at the time. We looked at eBPF, which now is it's become everyone's cup of tea, so to speak. And we built a fabric out of eBPF and 2 implementations. One using the DPDK API and one using sockets to demonstrate essentially arbitrary packet matching and processing with all the rich semantics that BPF gives you. And we build an architecture here, different BPF maps that allow you to define different tables, and also complete with a control protocol that basically allow you to program the control logic in a high-level language and then compile down to eBPF elves and install through operations of a control protocol to the programmable switch. So the reason I'm saying this is that at the time we also looked at how good this was, and we compared it at the time with OVS and the behavioral models that were available with P4. And here you see a comparison of a basic learning switch and how it performs, how it scales up to 10 gigabits per second using the different technologies, or it doesn't scale to 10 gigabits per second using the different technologies. And here you see BP Fabric implementing different functions, starting from a wire function that goes straight up to 10G. It's a learning switch, and then a function to compute the arrival packet size distribution and an EWMA algorithm. You see these are the different implementations of DPDK and socket implementation and how they scale. So, not too bad, but also, of course, this is an environment with no hardware acceleration to go really full speed. So programmable data planes are great, but we build them for the sort of general the general purpose processing that we expect for packets. So what about if we want to facilitate specific type of processing, in this case, cybersecurity, in these kinds of devices and environments, again, without having the luxury to afford hardware acceleration. So we looked at how we can construct essentially programmable and therefore extensible cybersecurity for these environments by actually building a service function chaining framework to take different individual or a number of network functions and put them in a chain to execute cybersecurity functionality. And this is the sort of typical pick any 3 problem. We wanted something to be secure, fast, and inexpensive. And obviously, you could pick any 2, right? So, we do have accelerated network stacks like DPDK, and we do have safe language or safer language tooling like NetBricks and other containerization approaches for isolation or hardware features like trusted execution environments. But these require support that you kind of see in sort of data centers, whereas the environments we're focusing on as part of this program, but also recently is the more low-end environments where you might find SBCs at the edge with slower CPUs, fewer cores, less RAM, and so forth. So we try to come up with a system to offer the cybersecurity functionality while reducing latency and also minimize power use. And of course, this environment, the only thing that works in our favor is that, you know, we need to sustain much lower data rates. So we explored the eBPF and the network stack bypass available in Linux for eBPF to do this, and trying to see if and how it would build inexpensive cybersecurity SFCs to run on the Pi. And you see here the sort of physical and logical dimension of the network stack and the various places where you can have hooks to offload functionality. So, you know, if you're coming through your Mac and your NIC, if you're operating a smart NIC, you can offload functionality straight here. And, you know, there are many models that support P4, eBPF, and all that. You know, DPDK hook, you can bypass the network stack here. An XDP, you got driver support, you can offload here. But what makes it attractive in this case is that because there is a hook where you can link to XDP after socket buffer allocation, this becomes more generic and does not require this support. And then if you need to pass on to userland, you've got the AFXDP that you can use. You can do this from. Now, that's great, and also the properties of eBPF, like for example, like also P4, I suppose, is that, you know, the functionality is relatively safe that you put there. It's length checked, and pointers and map accesses, execution time is bound. So this from a safety point of view, I guess are positives. But then in these types of environments, you've got the problem that NICs only expose a single RxTX queue. So parallelism of what you can do here is limited, right? And then you're hit by these tail latency spikes and throughput losses. So with all this in mind, what we did is devised Galette, which is a hybrid XDP and userland solution to build these SFCs. And so you see here, the idea is to divide traffic between the XDP and userland. So for example, if you have a chain that consists of an ACL and then a rate checker, and a DPI and a statistics module, okay, you can choose, you can form the chain and choose what runs where. You know, what the bottom layer of this diagram shows is you know, that modules A, B, and D from here can run on the XDP fast path, whereas module C would run, the DPI would probably run in userland, because if you did run the DPI on a single core on a single queue in the fast path, you would be clogging up packets coming in through the interface. And so we built this framework to compile to both eBPF and native code for the different systems and be portable across them, and try to facilitate, as I said, low response times as opposed to high throughput. Okay, so the chains were built by putting together individual crates written in Rust, and then use this TOML syntax to define the chains and the maps, and also you know, say which function runs where by you know, disabling XDP explicitly or implicitly. So for example, what happens here is that you see here that packets have entry and exit points for each of the from each of the functions. And you know, packets that would go through a relatively inexpensive ACL here, this would run as part of the fast path. Then so would a lightweight rate checker. Now, if a packet after those two functions needs to be processed by a DPI module, would have to go to userland, and if it does, then it runs to completion. So we don't down call in order not to put extra weight back on the receive queue here. If it doesn't, it would stay on the data path, on the XDP data path after the rate checker, and the stat module would then send it out to TX, unless of course any rules of here would make it drop. So what can we see here? It's a couple of graphs. There is many more details and graphs in this paper we published recently in IFIP networking. So what we see here is SFCs running solely on XDP or using the AF XDP path to go to userland, or everything runs in userland through AF packet. And I guess what we see is the sort of big difference in latencies from AF packet when we accelerate, and then the differences depending on whether we use this userland XDP split or not, and whether we use polling or hierarchy. In terms of throughput, again, what is interesting here? So these experiments, this graph here is running on the Pi. Here we compare the same SFC being executed on the Pi and on a NUC, and you see how the throughput reduces as the probability of executing an expensive NF like a DPI increases. Okay, and how it reduces? It always reduces, of course, but also what's the difference between upcalling, which is the dashed lines, and not upcalling, trying to execute everything on the data file. You see this especially here, sort of dramatic drop in throughput. Right. So just checking how I'm doing with time. So this type of work we're hoping to extend and enable this instrumentation of these relatively lightweight or resource constrained, if you like, environments. And what are the sort of things we might hope to find, and we might hope to be able to discover and then do some detection. Okay. And another thing we've been working on, which at the moment is not integrated with any sort of programmable data plane stuff I talked to, but this is the sort of this is the idea that we will manage to, was to essentially fingerprint PLCs and memory attacks in PLCs and industrial control systems. And again here, so PLCs are controlling or interfacing, if you like, between the digital and then on the other side the physical processes. And they have been targets of attacks recently in the Iranian steel manufacturing plant that I showed the short video clip before, but also in the Florida water treatment plant in 2021. And the problem is that you can have different attacks resulting in the same outcomes, and therefore by looking at the outcome, you cannot say what sort of an outcome. So you can force a water pump open by brute forcing a PLC or by manipulating the ladder logic. Okay. The outcome is the same. So we've looked at a space where we thought not much work had been done, and it was looking the PLC memory artifacts, so both the state of registers and also the application code, and try to use this to detect and classify different types of attacks to PLC memory. And here you see an architecture of what this was. So we were doing this by acquiring data from snapshots of registers taken at different points in time, and building the MRL, the master register list of a PLC, and then also inspecting the application code and creating then a fingerprint out of combining those other artifacts, what we call a PLC memory register map, and then try to run some attack detection and classification algorithms on this data, based on deviations from what we call a mapping condition of the registers, that basically tells you the difference between what you see in parts of the application code of the PLC versus the particular state that the registers of a PLC might be in time. So just looking at this in terms of the design, so the PLCs have 5 different register areas in terms of inputs, outputs, holding timers, and so forth, and a number of registers under each category. And this depends on the on how many, depends on the type of a PLC. So there's a bit of a process in order to discover this and build this, this base of what your asset is. And then, of course, because of this difference, also it's important to examine, whatever you do, to examine whether it applies to different types and models of PLCs. So with this so the register areas, you can take dynamic snapshots, and in each of these dynamic snapshots, you will have a bunch of active and inactive registers in each of the input, output, and so forth areas. And at the same time, you've got the function blocks in your application code that define the sort of static instances and which registers appear or exist, if you like, in a specific static instance. And then these two are combined. So you build first all your static instances, and then you timestamp this as time 0. You repeat the dynamic snapshot of your register enough times to build your baselines, and then you come up with what we call the PMRM, the PLC memory register map. And this map records, as I said, mapping conditions, which is kind of a truth table. And these different 4 conditions is whether a register exists in a specific static instance in the PLC application code, and whether it's active at the current snapshot. So 00 means that it does not exist and it's not active. 01 means it does exist in a specific static instance of the application code, but not currently active. It is currently active, but does not exist in the static instance, and so forth. And so we evaluated this. So I just don't go through all the detail in this slide. We evaluated this over an emulation of a water treatment testbed that we have here in Glasgow, which comprises different sensors and actuators to emulate the different phases of water filtration, disinfection, and so forth. And this is the sort of environment that we emulate. So it's a single PLC environment with an HMI and then a switch that connects it to a supervisory network, and then the enterprise network, and so forth. And we can switch these PLCs to be different models. And we looked at creating patterns that resemble different types of attacks from the MITRE framework, both static and dynamic, such as program download and program modification and so forth. And you see here, these types of attacks were observed in different real attacks that have happened against ICS infrastructures. So, say a little bit of what the results tell us. So we use one class SVM and k-nearest neighbor algorithms to do attack detection first, and we saw that there was good generalizability in the sense that we tried both two PLCs and we got high scores for both. And then we started looking also at the different mapping conditions that I described before, that we can see here in terms of their density functions, but also in terms of the clustering between different mapping conditions. And this is for an Allen Bradley PLC, and this is for an S7 PLC. Okay. And from analysis from this, we see that certain combinations, for example, the combinations of MC2 and MC3, which is the sort of 0110, whether you have something in specific function block and it's not active in the specific snapshot, and vice versa. Gives clear separation of clustering. And see here, you see the distances in the CDF of the deviations of these mapping conditions. We did a bit more of classification using a number of algorithms. So five classifiers: linear regression, KNN, Gaussian, naive Bayes, and SVM, and random forest. And again, trying to see which of them behaves better. We also devised a feature set by taking combinations of the different mapping conditions. So the four of them individually, but also combinations of all 4x2, 4x3, and so forth. And again, we see that it's a combination of MC and MC2 and MC3 seem to perform best. The MC4 alone, the mapping condition 4 alone, seems to perform worse. And here's a few results that given an idea of how long it takes to do this kind of classification of the different algorithms. And it's with a full feature set and all MC variables, it's on the order of under a second most of the times. So these are the this shows how well the promise, but also the challenge of looking at different types of data and trying to make sense out of different types of data, and doing so, or finding ways to do so in a running environment which is relatively resource constrained. So what we're looking forward to do is to advance those systems, but also work on the sort of intersection, if you like, of these areas, and also of the different phases of the resilience framework, and the NIST framework, and so forth. So I think I'll stop here and show you another couple of slides. You probably know we're recruiting, so I'll take advantage and say, do a bit of a promotion of the school and our group. So we're recruiting for 2 faculty positions at professor and LSL and reader level in cybersecurity, and also in my group, I'm recruiting for postdocs and currently trying also to fill 2 PhD studentships rather. So if you want to help us make this growing the scale of this and similar work, please come and join. Also, please go and read a fresh article that we've got published at IEEE Communications Magazine. Should be in the November issue about digital resilience engineering and how it needs to be built in, rather than bolt on in future systems. So with this, I'll thank you very much, and I'll stop.
Nice. Thanks a lot, Dimitris. There are a few questions in the chat. I don't know if Spiros you'd like to say it, or shall I read it out? Or Dimitris, you can also read the chat. Then there are a few questions by Andrew.
Yes, hello. Hi, thank you very much for the interesting presentation. My expertise is mostly on power systems, so some of that is a little bit unfamiliar. I was interested in the network science sort of. You mentioned clustering. We try to use not clustering specifically, but other metrics anyway, on about kind of trying to identify vulnerabilities and hotspots, or points of vulnerability. What's your take on that?
So I think you're referring to the graph-based work, and this is pretty much work in progress. So I couldn't. So you've seen these pictures that look at certain metrics, distance metrics between different artifacts, but I couldn't tell you now which one to go for, whether we've got a winner. We're still working on it, and trying to write a paper. Now, in terms of the more sort of more traditional classifiers that we've used in other parts of the work, we've seen that KNN works quite well without needing too much training data and sort of across the board various metrics. But again, I'd probably say that it's hard to generalize, and I'd be interested to know your experience. You said you're coming from a power domain, and something I didn't say is that we also have a new project just started last month on the cybersecurity of power networks and cross-country power transmission and distribution networks. And again, I'm not confident to say what mechanisms generalize to which other systems. I'm very cautious here because the physical processes might be quite different. So, and what I mean is that even if you're looking at PLCs that are operating on the same physical process, even though we try to generalize across PLCs, quite a lot depends on the type of configuration you have. So even for the same physical process, if you're running a different wiring topology or a different network topology or you operate the same physical process using a different number of PLCs, these things might change. So yeah, this is a sort of there's algorithms that have good generic properties in terms of how much overhead they require, or how less overhead they require, and how accurate results and F-scores they give. But I'd be very cautious to say whether this generalizes across different domains. I guess to a certain extent, as far as theory goes, I suppose, yes. But it remains to be proven, I suppose.
Thank you.
Cool. I think we are coming close to the end of the hour. But Andrew had a bunch of questions. Andrew, I don't know if you wanted to channel your inner GPT mode and summarize that into a quick question.
No, I don't, but I'll pick one of the many. So that was really good fun, but I was wondering, where did the networks and PLC, because they're two topics, but they're not really ones that necessarily look the same. Did they rise because they're your interests or partner interests or somewhere else? Because they sort of maybe share some dissimilarities, like the power engineering versus something else.
No, that's a very good point. And it's a bit of both. So it's obviously it comes from my interest being in networking, but also the realization that the network is the aggregator. So all these topologies and that get connected together via the different layers of the Purdue model and all that. And if there is a place where we can have some instrumentation and some functionality that could potentially be integrated with this kind of detection, this is the network. You cannot do it on the individual PLCs, or maybe you could, but in an ideal environment. But they're not, they don't have these kinds of capabilities. You're then changing the whole system. Monitoring of these infrastructures again come from their different networks, the OT networks. You cannot run a monitoring process on a PLC. You have to use either a tap or a passive tap or a span port on an industrial switch. So I think this is where it comes from. I do acknowledge what you say, that at the moment it appeared as separate work, and to be frank, it has been. It's sort of the work that led us to make the case that we should be looking at these things together. So yeah, hopefully I'll have something more integrated. I or my team will have something more integrated next time.
All right. Okay. On that note, I think we'll have to stop. Thanks, Dimitris, for the great talk, and look forward to seeing you again when you have some further results.
Thanks, everyone. Thanks for attending. I'll try to save the chat, and I didn't have the time to look at all the questions here. I'll save the chat and see if I can get back to you individually on any sort of individual points.
Yeah, I
Thanks,
can
everyone.
also send you a transcript of the chat.
Great.
Take care.
Thank
Bye.
you. Cheers. Bye. Have
Thank
a
you,
good
Demetrius. Thank you, everybody. Bye.
Cheers, guys.